1, 2, 3, 4. Hiya. Hiya. Hi.
Yeah, just trying to get the camera and microphone working.
Oh, fantastic. I can see some pen and pencil.
Yeah. Yeah, everyone is not here as yet. They'll be here in a minute.
No problem.
One of the members of our team is at home, so that's his name. I think.
Oh, right. Okay.
Yeah.
Cool. I'll just share a slide to start off with up here. Oh, and Marco's joining as well. Oh, now I can see the glue sticks, I think they are. Oh, hi, Tommy.
Hi, Rog.
How are you?
Fine, thank you. Is this nearly your last day of term?
Yeah, so tomorrow we're with our tutor groups and we're doing and hiring and assemblies and things like that. So we just had our last lesson of the term.
Oh, right. Great. Is Christian there?
Oh, hello, I can see someone.
Is that Christian?
Hey,
It's Tommy here.
we can't hear you.
Can't hear me.
I can't hear.
Just coming.
Oh, there we go. Oh, we can hear you, Tommy. It's
Yeah, I can hear you.
and Marco, I can see you as well. Hey,
Yeah. Hiya, Mark. Is it Mark? Marco?
Yes, Marco.
Marco.
Yes.
Hello, I'm Tommy. I'm just the chairman of Physics Partners.
Nice to meet you.
Fantastic. Are we waiting for any more staff, or what should we do? I suppose the other thing we can do while we're waiting is there's some interesting pictures on there. I suppose which of, if these were your students, whose answer do you think was the one you'd prefer them to have? And what would you do as well in terms of if there's any misconceptions, how would you teach to those misconceptions? So you've got some pictures there. If those were your students, which do you think is the best answer? And if you can see any misconceptions, what might you say to those misconceptions? Oh, I can't hear you, no.
Can you hear now?
Yep. Yeah, we can hear you.
Yeah,
Yeah,
good. Okay. Yeah. The mic is on now. Fantastic. All
Okay.
right, because I was wondering if you're able to hear. Okay, Christian is here now.
Oh, good. Okay.
Around camera this way.
Can you hear us, yeah?
Yeah, we can hear you.
Okay, hello, Raj, how are you?
I'm good, thanks.
Good, I'm all right. Is that
Oh, I can't hear you now. Yeah, I can hear you now.
okay? You can hear us, yeah?
Yep.
All right, that's great.
Stop on the back and books.
All right, let's do this.
Yeah? All right. Look.
It's frozen.
Yeah, but we're fixing the camera.
Just a minute here, please. Let's.
No
Sure it's
problem.
not.
Which camera?
I replied in the chat. If
You're using the
Yeah, I did
Want to read?
see, Marco.
That is the one that gives you
Yeah,
problem.
so you said the bottom left, it looks red because it reflects the red light and absorbs the rest. I think that's a nice one. So what about the person with the white t-shirt? Absorbs the red light and gradually releases it. Would you say that's wrong? And if you think it's wrong, I suppose what would the teaching strategy be to correct that misconception?
I am not sure about the gradually. I actually don't, I'm not a physicist, but I don't think gradually is correct.
I would agree with you. I don't think gradually. So what could we do you think? What would you do in your classroom in order to correct that misconception if one of the students said it?
I think if the students say gradually, it didn't really understand how wave move.
Mm. So what kind of teaching strategy might we go for in order to hit that misconception?
Maybe draw, how does it work?
Or I'm thinking about it, maybe doing a demo in which you shine the light at it and then maybe you just turn the light off And you say, is it still emitting light?
Yeah, because you're right. If it's gradually, you will
then
be
it will
able
still
to kind
go
of like.
after you turn the lights off. Yeah, I think the one in the pink top, the rose looks red because there's red light and sunlight. I think that's okay as well. I think I'd prefer the one with the in the bottom one that you chose. I think the pink would be my second. But I think maybe what you would do there is you would try and pass sunlight through a prism, get a rainbow, but you could also show that you can get rainbows off of house lights and things like that. Just looking rightwards. And so that can be interesting in terms of giving some ideas into spectroscopy if they're doing a bit of chemistry later on, if they're keen to take chemistry A-level.
Yeah.
We can do that. Or even go with the burning metal salts and having those different colors. And so that can
Not this one.
do that.
I mean,
What about the-
technically, there is a little bit of truth in all of them. But
Yeah. I would certainly say none of them are completely wrong. I think the one with the yellow top, it looks red because that's what color it is. Maybe, I'd struggle to argue with that. I'd maybe ask for a little bit more insight, but I would struggle to argue with that. I suppose with that person, it'd be interesting to shine a different color, say blue light. Yeah, we can hear you.
Yeah, they can hear.
Oh, you can hear us. Okay, that's good.
Yeah.
Okay. All right. And can you see what I'm doing?
Yeah, I can see your hand going past.
Oh, okay, perfect.
So let's
All right. Well, there's technical difficulty there trying to sort out the camera and the mic. Okay.
Miss, if we can all sit one side, please, so that it's easier.
All right. Cool. Yeah.
All right, Raj, sorry for the little delay. As you said, we're trying
I'm
to.
gonna adjust from my computer because we can't see some of
You can
we can't see that.
see that.
No.
That means I need to forward it to you then. Let me see if I can forward it to you on my phone. Okay, so we can get started. Yeah, right, you can hear me, yeah?
Yeah, I can hear you. Is it too small, the pictures?
You can see the four of us?
Yep.
Okay. Okay,
Yeah, I can
two
see
other
Courtney in the classroom and Marco at home.
All right, yeah, we still got Shakai who will be joining us from this in a meeting at the moment, but once he finishes the meeting, he's going to be joining us from home.
Shall we get
already
going
said-
and then they can join us in the thing, because I'm mindful I don't want to keep you past 5 because I'm sure you've all lots and lots of things to do this afternoon. So shall we get going? So we had a look at this kind of starter task. So these are called concept cartoons, and they're published by the ASC, by Millgate House. And they're quite nice to kind of start a conversation. So you might want something like this, and you might want to ask students, who do you think's right? And just like we asked you, what would we say to somebody that we think is wrong? So how might we correct their answer? And these are quite nice because they're speech bubbles. Students seem to feel quite happy to say, okay, they're just people's opinions rather than facts. So today we're doing a session on waves. I'll just introduce myself and then we'll start off with some diagnostic questions and then go on to some ideas about how to teach waves, sort of really at Key Stage 4. I can kind of touch into triple science and Key Stage 5 if you like, but we'll see how we go. It's only us, so it's only a small group, so feel free to stop me, to interrupt me, to ask me to elaborate, or ask questions, if something doesn't make sense, feel free to just kick in, okay? Yeah, so let's go for it. So my name's Raj. I'm a teacher at Dulwich College. I'm also chair of the London region of the ASC, and I'm a lead facilitator for STEM learning. I actually started my teaching career in Harris. I was based at Harris Crystal Palace, and I became ESS for for the Harris Federation. So I used to work with, I don't think Fiona and I don't know if Griff is still there or Bill Dodkins. So yeah, I used to work with those guys. I then went over to the Science Museum for a bit. I was head of physics at Seven Kings in Ilford, which is a comprehensive in Ilford. And we brought the ALPS scores up there. I worked a bit for the Institute of Physics. I then worked in Stockwell in a school, I think we were 95% pupil premium. But there, and I was a senior leader in there. And then I've most recently worked as part of the executive leadership team for the small multi-academy trust based in kind of Bromley area. So when it comes to talking about waves, what I really like to do is throw some diagnostic questions at the students. So it would be interesting to have a think about with these questions, not only what you think the right answer is, but also what the students would be saying as well with that. So we've got a situation here, we've got a wave on the ocean, and it's making the ball move up and down. And so this wave is transferring energy to the ball. And the question I would ask the students was, which wave transfers energy to the ball most quickly? So do you want to have a think, maybe even have a chat out loud? What do you think is the correct answer? And then what do you think is the most common incorrect answer that students would say?
Again, as a non-physicist, I'd like to try.
Yeah, go for it.
I think B is the one that transfer energy most quickly. I don't know why I have this feeling.
Okay.
Doesn't mean that it has more energy, just quick. I'm thinking the difference between more energy and quickly.
Energy most quickly.
Because not necessarily the one that have more energy will transfer more quickly, I guess.
What about, does anyone else have any other ideas for that? And also, what's the most common incorrect answer?
I go with D because of the amplitude.
So we've got a nice smaller amplitude in D.
Yeah.
Yeah, so that would get more energy faster, in my mind.
What about frequency? How does frequency affect it?
There's more waves are passing.
Oh, more.
More waves are passing.
Yeah, so there are more waves passing in C and D, aren't there, than in A.
Yeah. Yeah, so
But A and C are the higher amplitude. So the amount that they go up and down is more. Okay, well, if I tell you, well, let's give you a second question as well. So we've got those along the top. If we ask students, one of the things you can do is you can ask students to justify their opinions as well. And before I tell you the answer, I'm going to hold you on tenterhooks and ask you what do you think are kind of the best answers here. Which would you love your students to give as to why they chose what it is?
the best answer for the question.
So which of those is the best reason?
But did you say which one is the correct one? Not
No, not
the
yet.
reason. Not the reason. The wave.
No, I didn't say that was the correct answer to the previous one just yet. I'm
All right,
leaving
all
you
right.
waiting. I'll tell you in 30 seconds.
I still think it's B.
I would say B.
This will make the ball move most quickly.
I think B.
Yeah. Because if the ball is moving most quickly, it means it has a lot of energy.
Okay, so you're saying if the correct answer is B, the ball, I'll tell you that is the best answer. The ball, this wave makes the ball move most quickly. Now, speed is distance over time. So go back to your 4 waves, the ones along the top, which one is going to move the greatest distance in the least amount of time?
Look, I'm leaning towards C.
Say again?
So I'm leaning towards C.
D. So, but the distance there is smaller, I would say, than A or C. I would say so the amount of time.
Yeah, C, not D.
Yeah.
C as in cold.
Our correct answer for the first one is C.
C. Yeah, that's what we're saying. C.
Oh, fantastic. So our correct answer is C.
Yeah.
Our
C as in yeah.
would be B. And the reason that we would say that is that we've got a large distance coming in there and
Yeah.
quick time. So we're moving in terms of distance and time, we're moving the bigger speed. The misconception that students tend to pick most commonly is A. And yeah, this is one that we see a lot, is A. And that misconception really comes from the idea that it looks like there's more stuff going. Those kind of waves look nice and big. So students tend to go from there. Now, it's interesting when we have a look at these, and the students that pick answers like A for one of the reasons, they tend to have ideas about whether or not the water is moving forwards or backwards, rather than just up and down. And I'm going to show you a simulation in a moment that we can have a look at the oscillations going up and down rather than moving forwards and backwards. Students will go and say, there's some issues with energy, and that's something to really unpick as well, is the idea of energy. Whereas D, again, we've got arguments around. So asking these kind of questions right at the start is a really useful way of really what knowledge our students have, and ensure that we tackle those, and also trying to work out.
Yeah.
Yeah, but if you like it's stricken out and some part.
If we have a look at another one, so we've got here water waves made with a plank of wood.
We're struggling to hear you. We're struggling to hear you clearly.
Struggling to hear me clearly.
Yes, please.
Okay, give me a sec. Is that better? Can you give me the thumbs up? I've just muted you guys. Does that help you? Yeah. Oh, okay. I think you're getting some feedback. So I've just muted you guys, and then I'll unmute you when I ask you for a question, if that's okay. So water waves are made with a plank of wood, and bigger waves are made by pushing it down harder. So the question here is, which wave moves faster through the water? And I'm afraid one of you might have to sit and drive the computer behind to mute and unmute yourself. So which one do you think moves faster through the water?
Which way moves faster through the water?
Or is it a trick question?
But what we think, why? We're going for why?
They said pushing down more makes the wave more.
Which wave move faster through the water?
There was something said about pushing down.
But
Yeah.
what did you say before about pushing down?
So that's how they're making a wave. They're getting a bit of wood and they're pushing into the water to make the wave.
Wave. I'm going for B.
Okay.
Me too. I think Y move faster.
Okay. So what do we know about the speed of waves in terms of things like the speed of light?
Speed of wave?
What affects the wave and even waves like light? What affects things like the speed of light?
One
What
speed.
is, I'm not.
All light waves move at the same speed.
Exactly. So all light waves move at the same speed. So all even radio waves move at the same speed. So when they're electromagnetic waves, they move at the same speed.
Yeah.
What about waves like water waves?
Longitude, water wave, water wave.
Water wave or two transfers.
They all move at the same speed.
No.
No, they don't. So what affects the speed of the water wave? If you had a wave that was going through jelly or custard or something like that, would it have a different speed compared to one that was going through water or something that has really no viscosity?
I think larger waves in water move slower than the smaller ones.
Okay. And why do you think that?
Because
System.
yeah, the larger the wavelength, the lower the frequency.
But
So you have
Yeah,
less
but
wave
the speed
time,
could be
to create a larger wave, you need a larger energy, don't you?
yeah.
Yeah, and then since you need a larger energy to create it, that means the possibility of it moving much more faster in terms of distance. Yeah, would still have that correlation.
So our wave equation is wave speed is equal to the frequency times the wave.
Wavelength.
So actually our amplitude is going to be independent of the wave speed. So both our waves are going to move at the same speed. As long as the water's the same, the depth of the water, type of the water, then actually this.
Oh, so the amplitude is independent of the wave speed.
Yes.
So the
Because
things
it's not
wave speed are going to be things like the type of water it's going through, the depth of water, but not really the amplitude. So this is going to be a constant, and it's to do really how those water molecules are hooking onto each other. How quickly that moves. I'm going to skip through a few things because I know we want to get through onto our simulation. So we can maybe ask students with strings, ropes, and things like that similar kind of thing, and go through from there. And I'll send you the slides. Let's have a look at the simulation.
I'm not here.
Have a look at the simulation.
Can come up, you think of the.
So one of the things that you can do to go through is to run this code simulation. So these are free to log in. They HTML5, so they'll run on the students' phones and things like that. And what you can do is that you can set it to oscillate. We'll get rid of the damping. We'll get rid of this clamp at the end. And we've got our wave here. And what we can do, rather than necessarily doing this initially practically with a water bath or something like that, these simulations are really nice and powerful because we can just pause them here. And we can ask our students, say, to have a look and say, okay, look at this green blob on the wave. And as we step it forwards, what happens to the motion of just that green blob? Yes, we know the wave itself is moving to the right, but what's actually happening to that green blob? What can we say is going on? And we might even want to grab a ruler and line it up with one of the green blobs. I hope this is the one you're looking at, but you can see here, students should be able to talk about how it's the green blob is just oscillating up and down, despite the fact that the wave itself is moving to the right. So we can start to talk about the fact that these waves are just oscillating up and down, but that oscillation is being passed on from one to another, to another, to another, to another, to another. That word oscillate is a great word to use, and it's a lovely word that we can encourage our students to use in their exam as well. So your exam boards tend to love that word oscillate because it means it moves up and down, backwards and forwards, again and again and again and again. So it's going to move up and down or backwards and forwards again and again and again. And it's a lovely word to encourage those students to use. And you'll see it does feature quite a lot on your exam marking scheme. So that word oscillate is a lovely one. So that's oscillating up and down, that green one. But our wave is moving towards the right. And what we can do is we can, even with a simulation like this, we can set up a timer. We can start our timer and see how long it takes for our wave to move a certain distance. And we can do a speeder's distance over time with that. And the nice thing about this is you'll always get a perfect answer because it just lives in the computer. And we can have a look and we can see how if we change our amplitude, like with that diagnostic question previously with the water wave, we can see actually the wave travels at the same speed, regardless of what the amplitude is. So the amplitude doesn't affect the wave speed. Things like the tension will. But the amplitude won't. The frequency, the number of times the wave goes up and down in a second. And if this kind of thing, you might want to think about your local buses that stop outside the school, and you might want to say, okay, the 268 is more frequent than the 119. And the students should kind of understand, okay, what does that mean if I say the 268 is more frequent than the 119? Oh, it happens, it comes more times every hour or something like that. So we can talk about that frequency, how many times our wave goes up and down per second. Marco.
Question. So here the frequency are the green dots.
No, there's
You may-
so the frequency is the amount of times it goes up and down per second.
No, I understand that, but what's the best way to visualize that? Because I thought a green dot could have been a good visualizer.
Yeah, I suppose you could. So say if we've got a frequency of 2 Hertz, we'd expect it to go up and down 2 times in each second. So let's reset our timer. Let's get our green one right at the bottom here. And we can start our timer. Okay, so it's gone up and down and up. And it's going to come up to 1 second.
Right. Okay.
Oh, I think I just mistimed it a little bit. But I'm sure if you're a little bit better coordinated than me, you could show that our frequency is up and down 2 times a second. And then if we increase our frequency here, that we can go up and down more times a second. And you can see the wavelength here, the distance between 2 waves is changing as we change our frequency. Okay. So the tricky thing that we will get in an exam situation here is, if we go back to our slide, we'll often get 2 graphs and they'll look very similar. So one graph will, they'll both have displacement. So how far the wave has gone up or down on both of them. But one graph will have the distance, the position, and one graph will have the time on it. And these two graphs will look very similar to each other. So students might find it a bit tricky to differentiate between the two. And this is where we start to introduce our rules about reading graphs in exams and saying, if the examiner presents you with a graph, the very first thing you can do is that you need to look at what's on the axes of these graphs. And when you look at that, you can see if we freeze it like this, this does look like one of the graphs here. These are individual separate little beads coming across. And so what we've got here is the distance along. So that corresponds to the top graph. So these little things are individual separate little beads that we can go along. So this distance from here to here, that will be equal to our wavelength. Okay, because that's an actual distance. It corresponds to the distance going across here. But we can also draw a graph. Let's get rid of that. We can also draw a graph of the motion of an individual particle. So we could say at time equals 0, our green particle is at our equilibrium position. And then it starts to go up. Until it gets right to the top. So that's at this time. So it's at this time, it's right at the top. And then it will start to go back down again. Until it gets to the equilibrium position, which is here. And then it gets all the way to the bottom, which is here. So this second graph, even though it looks like the exact same shape as the first one, obviously I've used the same image there, because we've got something different on the axes, we're actually plotting the motion of an individual particle. And so this distance from here to here is a value in time, and that's the time period rather than the wavelength. And this can sometimes catch even some of our most able students out. It's because those two graphs look very similar, but we've got different things on the axes. That distance from one peak to another distance either represents the physical distance between lots and lots of different particles, or if it's a graph of the motion of one particle, that's the time period. Does that make sense? Are you happy with that? Yeah, I can see some nods. They're fantastic. That's great. Okay. The next thing I would do, so once you've got students kind of happy with these kind of waves, you might want to use the simulation. You might want to use a slinky or a rope or something like that to kind of simulate them. If you're using different analogies, what I love to do is I love to mix them together. So using the slinky and using the simulation and using the rope. And if you've got a really kind of open class, what they can do is they can even do a little bit of metacognition with you and say, okay, which was the best way to teach you? I taught you in 3 different ways. Which was the best way to kind of get the idea across? And that's a really nice empowering thing. I think that's at the moment, that's right at the top of the EEF's toolkit in terms of teaching strategies, is promoting metacognition. So a nice way to do that, show them a couple of different ways of explaining it, and then get them to interrogate their own understanding. Then I think what's quite nice is that we're always really itching to get on to talking about the electromagnetic spectrum. But what you can do is rather than just jumping into the deep end and say, okay, right, we'll learn the order of the electromagnetic spectrum, is I would spend a bit of time talking about sound. And do you want to have a go at scanning one of those QR codes? Maybe try and one person scans the red one person scans the blue one. And you'll get some interesting websites coming up. Maybe scan a different one. So what you've got, I think the blue one is a page from Wikipedia, and it's a image library of pictures that have been taken with an ultraviolet and an infrared camera of flowers. The red one is a photographer, a hobbyist photographer who does the same. And he's got a nice gallery of those things. And you can start to talk about the idea that, okay, what these images are is these are colors of light that we cannot see. And students might have a little bit of resistance to that. They might say, how is it possible that we've got colors of light that we can't see? But what I would suggest is that you have a go with talking about, well, there are sounds that we can't hear. There's quite a good correlation. I won't play this video because it will drive us all crazy, but it starts off with a really, really low sound that none of you will be able to hear. And then that pitch will increase and increase, and we'll all be able to hear it, and it'll get to the highest noise, and maybe some of us will start to show our age and not be able to hear it before the others. And there's a really good correlation between the pitch that you can hear and your age. So that makes a lovely homework, is for students to play something like this YouTube video on their phones to different members of their family, and then have a look and see, okay, right, can you hear it? What's the highest noise you can hear? What's how old are you? And graph those two. And you can show them that actually, as we get older, we get a little bit less sensitive to those noises. As an interesting aside, some of them might even find out about the mosquito ringtone. So the idea for that is, this is a little while ago, what do you call it? Shopping centers and things like that used to play really, really high-pitched noises to deter teenagers from loitering outside. And the teenagers were very, very smart. So these are noises that only the teenagers could hear. They're so high-pitched, they'd be very annoying, but all the old people would not be able to hear them. So what the teenagers did is they recorded this on their phone and set it as a ringtone. So they had a ringtone that adults couldn't hear, but teenagers could. So the teenagers quite like that little story. But they tend to really accept the idea that there are noises that we can't hear because the pitch is too high, the frequency is too high. So when we can then bring it over to our electromagnetic spectrum and say, okay, right, our middle one, we've got colors that we can see, but then if we go a little bit beyond that, there are colors in which the frequency is too low or the frequency is too high for us to see. And because we've been talking about the fact that there's sounds we can't hear, they seem to be a bit more open to the idea that there are colors of light that we can't see. And the benefit of teaching it in that way is that every time you then talk about something to do with light, whether it's reflection or refraction or something like that, because they realize that these are all just colors of light, they can apply these to these different circumstances as well. So you might get a question in which students are asked, a star explodes and it gives off visible light and it also gives off radio waves. Which one gets there first? And it's a trick question because, as you told me before, they travel at the same speed. And because they know these are just different colors of light, then they've got a better idea that, okay, they travel at the same speed. Or you might have something about reflection and you only got a chance to teach about visible light reflecting, but they'll also understand that infrared reflects as well, or ultraviolet can be reflected as well. It's a nice thing to have an explore of that. Do you want to have a quick scan of this other QR code? And you should get a PDF from the Institute of Physics. And if you have a look at between pages 4 and I think I've written 47 down there, we've got all of the different electromagnetic spectrum and some little stories between them. What I've done is I've sent my year 9s away with a different page, and I've asked them to just make a little poster over Easter about that. And so when I stick my electromagnetic spectrum on the wall, firstly, each of the students will have a stake in it because they've each built a bit of it. And they'll also have a nice little story that's maybe a little bit more applicable than just saying, well, radio waves are used for this, and so on and so forth. So those are some really nice little stories that you can have a look at. So that. Okay, I'll give you just a moment to have a look through that PDF. There's some really nice stories in there. Right. So our last two little bits to go through. Refraction. Oh, have you found a good story? Do you want to unmute yourself in the classroom if you wanted to respond? Good story.
Oh, I was reading about the X-ray of an author. He's talking about Mark Twain and Tesla.
Oh, okay.
Yeah, that one is interesting.
What I did is I physically cut them out. Gave different students different stories, and then got them to research it or do a little presentation or something like that on them, just for homework. And it's quite nice to get it. It kind of humanizes a lot more. So it's that science capital based, which works really nicely to engage, especially those students who kind of come to you and say, "Science isn't for me. It's not my kind of thing." Quite nice to do scientists are people and things like that. You can go for there. So it's quite nice. The last kind of couple, I'm sorry to whiz through, but I want to give you some time to have some questions as well. And of course, Tommy, I'll make sure everyone does their feedback form as well. Is this idea about refraction? And usually when you're talking through refraction, it's quite nice to talk through the idea of this analogy of soldiers marching forwards. And those soldiers are all marching forwards in nice straight lines. And they get to a field of wheat, and that makes them slow down. And so our first soldier slows down, the next one keeps going a bit faster. But then when they get into the field of wheat, they have to slow down, but the next one along still carries on going at a normal speed, and so on and so forth. And what you can do is you can start to draw a dot to dot connecting those soldiers' heads and say, okay, we're going to go in a nice line as straight as I can draw in my laptop, a nice straight line here, and then a nice straight line coming across here. And we can see that the angle has changed of that line. And for our students, because we're still talking about soldiers, it should be quite straightforward to ask, okay, why have they refracted? Why have they changed direction? And in that way, I would, I would introduce that and start to talk about changing direction there. It's because they've changed speed. And because they've hit that that material, that different material that's got a different speed, they've hit it at an angle, then they've changed direction. And when they've come back out, they've changed direction coming out. And once they're happy with that, and I noticed quite a few of you have got some laptops in front of you, I would suggest grab the either through a simulation, or if you physically got light boxes and things like that, get them to pop over to PhET again and have a look at the refraction sim. Now, when you use PhET, if you click on teaching resources, oh, I've got to sign in first. If you click on teaching resources and activities, you'll get a load of differentiated worksheets for them. And these are lovely if you've got a kind of computer lab lesson or something like that, or you get the laptops out. You can give different students different worksheets depending on their ability level and also how they learn. So maybe they quite like it where they're given a load of instructions and they follow it, or they, that's quite a minimal one. Or they might want one that's a little bit more structured and take them through something like that. They've also got some translations as well, which might be useful for you. But I think when I go through refraction, it's quite nice fun just to give the students a chance just to play and chuck in loads and loads of different things going on there, and make of those lasers going on in there, and have some goes, or maybe even if they're particularly talented, they might be able to spell out an initial or something like that. Probably a little bit easier to spell out your initial if your first name's Isaac. Difficult to make that letter in there. But either way, I think I would spend a bit of time just allowing them to play around and have a go and see what happens with that. See what happens if we get some white light. See if we can get a decent rainbow coming out as well. Before then moving on to that mathsy side of things and saying, okay, we're going to go back and have a go at doing our Snell's law experiment here, where we can look at refractive index and things like that, and have a look at how our speed changes from one medium to another. So I would really encourage you to give students a chance to have a play with these, and yeah, literally play and mess around and make some interesting things before spending that learning time moving towards actually taking some measurements and doing this core practical of Snell's law coming in. Okay. And our final one is when you round off your waves topic, particularly, are you guys doing triple science? Yeah. So you might need to have a look at black body radiation, or looking at emissions and absorption lines as well. And again, you will have done something like this in chemistry, where you're burning metal salts. In these cases, they will be probably dissolved in an ethanol solution to burn like that. Some people put them in spray bottles and they're quite good fun. But you can link these emissions lines to electron shell structure. And this is a really nice way to do it. And the way I tend to do it is I tend to tell them the story about, okay, it's lovely to see you come back after Easter. I hope your Easter was good. Us science teachers, we had an awful lot of work. What we did is we all got sent over to the nearest star, because we wanted to be able to know what the nearest star was made out of. So we went over to work out what these stars were made out of. We went over there in our rocket, in our special rocket for our school, and we took a big scoop of the star and took it back, brought it back to the chemistry department, put some universal indicator in it, and we were able to work out what stars are made out of. And your students will start rolling their eyes and saying, yeah, right, sir, yeah, right, miss. I don't think that's what you did over the Easter holidays. And then you can say, okay, well, if nobody's actually been to a star, what are stars made of? How do we know what stars are made of? And you can start to talk about the idea that the only thing that we know that comes from a star, the only thing we get is the light. And so therefore, any kind of analysis of what stars are made of, in order to do that whole unit in physics where we talk about red giants and white dwarfs and things like that, the only way we know that is that we've looked at light. So we need to use this kind of analytical tool to look at light. And the way that we know what stars are made of is that we look at the emission spectrum from a star. So we split the light up into its different lines, and we look at the emission spectrum of chemicals in the lab, just like when we did our burning metal salts. And it's a matching exercise. Our burning metal salts are have a set of stripes, and our stars are a set of colors, and we can match those from one to another. And in that way, that's how we know what stars are made out of, rather than us actually have been to a star or anything like that. And that's quite a nice kind of little story to take the students through for that. And then we can start to move on to black body radiation, and start to, even if we've got some really, really bright students, have a look at what should be our black body curve coming out, and then how we've got different bits missing from our curve because of absorption going through the atmosphere, and how that's linked to the gaps between electron shells that we've studied in chemistry. Okay, that's a bit of a whistle-stop tour through waves. If you want to have a look at any kind of topics in a little bit more detail, I'd be really, really happy to have a look at diaries with Christian and see. I think also when our year 11s and year 13s are off, I should be able to pop down the road as well. But it'd be really lovely for me and Tommy if you were to fill in this form, this feedback form. And I'm under, I think to choose me as a trainer, I think you do have to click on other and write my name in. So it'd be really great if you can fill that in, and then feel free to unmute yourself, and any questions that you've got or anything like that, go for it.
I'm trying to open the link, but maybe I scanned this better.
.com/evaluation.
Okay, I'm gonna try to use the, I don't know the name of the code, QR code. There
Okay.
you go. I have a little question.
Yeah.
It's something I say, and I think it might be wrong, to my year 7 student. Is the amplitude in terms of sound the volume?
Yeah, it's linked to the volume. Yeah.
But it's not just the volume.
Yeah. Yes. So I think I would say the amplitude is the volume. Certainly.
Okay.
I'll be very happy to say the amplitude is the volume. As the volume goes up, the amplitude goes up.
So as I learned today, if my pitch is the same but my volume is different, the result of the speed of the wave of the sound is still the same.
Yeah, so the speed of sound is determined by things like the temperature, the atmospheric pressure. So the speed of sound is different if you're going to go at the very top of a mountain or up where airplanes fly, or the humidity and things like that. But it's not affected by things like the frequency or the wavelength.
It's not about the frequency then?
No, nor the wavelength.
Okay. So if I shout with different volume, technically people don't hear me earlier?
No, I'm afraid not.
Or with a different pitch? No, just a curiosity.
Yeah, no. So with a different pitch, no, it doesn't travel.
I see. Okay.
Speeds. What's the reason I was a little bit cautious about saying amplitude and volume is that we have different sensitivities. So the human ear is really, really sensitive between 50 hertz, sorry, yeah, about 20 hertz and 2000 hertz. Or 20,000. If it's, you can shout as loud as you like. And if that pitch is higher than the human hearing range, all the dogs in your neighborhood will get really, really annoyed, but you wouldn't be able to hear it. And the same is true for things like microphones and headphones as well. So if you're buying your kind of posh Beats by Dr. Dre headphones, they've got really good bass response. So you will be, if you put a kind of bassy noise through at a certain amplitude, it will play it louder than if you put a high pitched noise. So that's why those are very good at kind of listening to bassy music, say with drums and things like that.
Yeah, because sounds, when we do sound, it is quite interesting how it's related to not only the wave, but how you hear it. It's not necessarily
There is
the
a
wave.
free, I don't know if I've got it installed on this computer, there is a free bit of software called Audacity. So you just download it.
Yeah, I know that. Yes.
You can have a good play with that, and that's also even used commercially. So if your students are interested, I think I've got too many things open. But if your students are interested in making electronic music or kind of making beats and things like that, then Audacity is, you can make it from scratch.
Yes. Yeah. No. I have Audacity. I play with it sometimes.
It's quite good fun, and the students might even use it if they're doing music GCSE.
Yeah. Anyway, thank you for answering my question.
Is there anything else you wanted to go through? Otherwise, we're happy to reschedule another session if you want to go through anything in a lot of detail.
No, I'm okay. I enjoyed it.
Fantastic. And anyone else who's in the classroom, is there anything that you wanted to ask or go through? Oh, I think they're just going around to unmute them.
Yeah, can you just, Raj, somebody has got a question there?
Yeah.
Actually put it in the chat. How would you teach them about ionization caused by waves?
Oh, say that again.
How would you teach? What strategy would you use to teach them about the ionization caused by waves?
Okay, ionization caused by waves. So that's a fun one. So I would go back to talking about these different these different metal salts, because I'll remember these from page 3. And you say, okay, how are we giving off light by burning these salts? And you can talk about your electron shells, electrons going up and down shells, and those electrons needing to go up a shell, they need to absorb a photon, or for them to go down a shell, they need to pick out a photon, and that's how that light comes. And if you absorb a photon of a high enough frequency, enough energy, then it will completely pick that electron all the way out of its shell structure. And so that's why, if we look at our electromagnetic spectrum, if we have these really high frequency waves, particularly gamma rays, maybe ultraviolet rays or X-rays, these are the kind of things that they have enough energy to promote those electrons way up that shell structure, all the way out of the atom. And that's how things are ionized, is that you're dumping enough energy in to because you've got these really high frequency waves. And so you're picking up of the shells. Yeah.
You okay?
Yeah, I gave him a thumbs.
Oh, thumbs up. Sorry, I thought it was a hand up.
Oh. All right, Raj, thank you very much. It's been a very useful session.
No problem.
There is no doubt that the team has been more enriched in terms of their strategies to be able to keep
Fantastic.
weight.
Well, I'll send these slides over to you tomorrow morning. And yeah. Good
Please,
stuff.
we really appreciate that. And then we'll now probably discuss among ourselves in terms of the next session.
Yeah.
Mode of delivery. Are we going to continue with online, or if we prefer face-to-face, we'll let you know by email, please.
Oh, fantastic. Good stuff. And then, of course, you're only down the road. So whether, I mean, we finish school at 4, but if it's easier for you to come here and if you want to use any of our equipment to have a go with some stuff, then you're obviously welcome to come up here as well.
Okay.
And we've got parking if you want to come up in a minibus or something like that.
All right. Thank you very much.
All
We
right.
really appreciate the session. Thank you.
All right.
Enjoy your holiday. Thank you. And Tommy, where is he? He's gone. Tommy, bye. I can't even see.
He'll be, I think he's just gone to France. He'll be back.
Oh,
All right.
All right. Thank you. Bye.
Bye.
Marco, see you later.
Yeah, I see you later, meaning today or tomorrow?
See, are you in tomorrow? Are you
Yeah, I can. I can come, so I will think I will come. Now I finally free.
Okay.
finally free.
All right. See you tomorrow then.
Yes.
All right. Cheers.
Bye.
Bye.
If you have to vote, sorry, Christian, if you have to vote, I vote to go to Dulwich College, which is quite cool.
All right. No problem.
I
We'll
like
talk
school
about that.
trips.
Okay.
All right. See you later.
All right. Thank you. Bye.
All right.
Bye-bye.
So I'm just going to chat to the computer screen for a moment. Tommy? Oh, Tommy, I've got a dash. I've got a train to catch. I'll catch it. I'll give you a call in a bit.